Welcome to today's Trane Engineers Newsletter Live program. I'm Jeanne Harshaw, and today we'll discuss trends in geothermal systems and ground loops. We'll start with a discussion of the various types of ground heat exchangers, including advantages and drawbacks of each, and how to size them. Then we'll move on to the heat pump equipment itself, contrasting distributed versus centralized approaches. And we'll spend a good deal of time describing various central heat pump plant configurations. We'll return to the ground heat exchanger and look at various system optimizations that can affect the size and cost of the Borefield, and discuss how to manage Borefield temperature drift over time. And finally, we'll introduce a few other newer system configurations and trends in geothermal. To cover today's topic, we have Trane application engineers Dan Gentry, John Murphy, and Ben Sykora. So John, can you get us started with an intro to geothermal systems?
Geothermal systems use the earth as both a heat source and a heat sink. During the heating season, the system pulls heat from the ground and moves it inside to heat the building. During the cooling season, the system removes heat from the building and puts it into the ground. But this is not an infinite sink or source. That's why the design of the system is so important and will be our primary focus during this ENL. Now, geothermal is intriguing because of its potential for achieving premium levels of efficiency. The ground temperature is more moderate than the ambient air. This means the compressor doesn't have to work as hard with less lift, so it uses less power. This benefit happens in the cooling season, when the ground temperature is cooler than the hot summer air, and in the heating season, when the ground is warmer than the cold winter air outside. Now, geothermal can also reduce stress on the HVAC equipment. Again, the reduced compressor lift means it doesn't need to work as hard. And the equipment can often be located indoors, protecting it from the harsh elements outside. Finally, geothermal may qualify for tax incentives or utility rebates. But like any system, there are some drawbacks. The installed cost can be higher, mainly due to the cost of drilling wells for the geothermal Borefield. And some buildings may lack space or land for that Borefield. So Ben is going to start a discussion of this system right there with the Borefield or ground heat exchanger. Ben?
The most important and costly part of a geothermal system is the ground heat exchanger. Let's start out by considering the factors that affect the size and cost of the ground heat exchanger. The ground is made up of many different layers. If you go deep enough, you'll run into oil, gas, and high temperature formations. Geothermal HVAC systems are typically installed in the first few hundred feet of ground, which is made up of different types of rock and potentially water aquifers. The size and cost of installing a ground heat exchanger comes down to three primary factors. Thermal conductivity describes how well the earth sinks and sources heat. Some kinds of dirt have better thermal properties than other types. Moisture content in the ground improves thermal conductivity, and underground water movement can significantly improve thermal conductivity. Higher values of thermal conductivity are better, meaning that fewer feet of borehole need to be installed. The labor cost of installing a ground heat exchanger depends on how difficult it is for the driller to get pipe into the ground. Hard rock layers can be difficult and slow to drill through, while sandy soil may be unstable after drilling and while installing the pipe. Local regulations may affect the types of ground heat exchangers that can be installed. Let's break up ground heat exchangers into four types. Horizontal ground heat exchangers can be the most cost-effective to install, but they require the most surface area. Vertical bores achieve high capacity with a smaller installed footprint, but drilling rigs are needed. Directional drilling can be applied to both horizontal and vertical ground heat exchangers. We'll touch on some scenarios where directional drilling could make sense. If local codes allow, underground water aquifers can be used as a heat sink and a heat source. Now let's look at some pictures to see what each of these ground heat exchanger types look like. Horizontal ground heat exchangers are generally installed with excavation equipment. The heat exchanger pipe can be laid down in a straight line or in a so-called slinky arrangement. As you can see, horizontal ground heat exchangers take up a fair amount of surface area, and the excavation process can be disruptive, meaning that you can't use that space while construction is in process. One option to limit the excavation needed for horizontal ground heat exchangers is to use directional drilling rigs. The drilling head can be steered up and down or side to side, achieving precision bore placement. Bores may be installed under a parking lot or an athletic field while that space is still in use. Bores may be layered at different depths, or they can be routed to precise locations such as the equipment room wall or an access vault. Vertical bores are installed by drilling a hole, inserting pipes with a U-bend at the bottom, and then filling the hole with grout. The grout seals the bore, preventing surface contamination from getting into the ground or the water aquifer. The grout also transfers heat from the pipes to the ground. High-performance grouts are available with additives that improve the thermal conductivity. The image on the right shows a cross-section of a borehole with grout filling the area around the supply and return pipes. Some drillers have low-profile rigs that can be used in an existing basement, and directional drilling can be used for vertical bores, allowing a large quantity of bores to be installed in a small surface footprint while fanning out underground to be in contact with a large volume of earth. If local codes allow, water may be pulled directly from the aquifer, pumped through the heat pumps, then returned to the aquifer at a different location. This open-loop geothermal method is called supply and reinjection. Assuming that the aquifer temperature stays the same, the system capacity is limited by flow rate of water that can be pulled out of the aquifer. Reinjection wells must be placed far enough away from the supply well to prevent recirculation. Be sure to check the local codes to determine if this type of system is allowable and if there are special design requirements. The State Department of Natural Resources may also have annual usage reporting requirements. Another way to tap into the aquifer's thermal energy is to use heat exchanger-based solution. The heat exchanger is installed in the ground, isolating the heat pump's source loop fluid from the aquifer. A pump in the heat exchanger circulates aquifer water, maximizing heat transfer to the heat pump source loop. This solution aims to achieve the high capacity of open-loop aquifer-based systems, but without the supply and reinjection aspects. Let's recap the ground heat exchanger types. Horizontal ground heat exchangers can be the lowest cost option if you have a lot of surface area or a limited system capacity. If the surface area is limited or the system capacity is too high, then vertical bores may be a better option. Directional drilling can help projects with extremely constrained surface footprint, or it can limit the excavation impact from horizontal ground heat exchangers. And if local codes allow, direct heat exchange with the aquifer can result in low-cost, high-capacity systems.
All right, so once we decide which type of ground heat exchanger is preferable for a given project, now Ben is going to explain how the size of that heat exchanger is determined. Ben?
Ground heat exchanger sizing should be done by a certified professional. If you need to find a certified professional, a directory is available on the International Ground Source Heat Pump Association website. Look for the letters CGD for Certified Geo-Exchange Designer, or GCSD for Ground Source Heat Pump Commercial System Designer. Let's get the flavor of ground heat exchanger sizing with an example vertical bore field. The first thing we need is a ground modeling software. GLHE Pro and GLD are common ones, but several other options are available too. Today we'll be using GLHE Pro. To use the software, we need to know 4 things. First is the heating and cooling loads for the building. Second, we need the thermal conductivity value for the earth. At the start of a project, we'll have to guess at this value, and later we can refine the model with a thermal conductivity test. Third, we need the borehole material specs, things like pipe diameter, grout properties, and fluid type. Last, we need some specs for the heat pumps, things like their efficiency curves and temperature limits. Once we set up the model and run it, the output is a value for the total feet of bore required. That total depth of 39,000 feet is distributed between a number of bores. In this case, we specified 120 bores in a 10 by 12 grid. 39,000 total feet of boreholes divided by 120 bores results in 325 feet per bore. If surface area is limited and the number of bores needs to be reduced, then we can look at using deeper bores. For example, we could reduce the number of bores from 120 to 96 by drilling each one deeper. That total borehole depth of 39,000 feet is maintained. Also, talk to the local drilling contractors. They will have important information to guide this decision. For example, if there's a setup charge per bore, then making each bore deeper could reduce the project cost. Or they could say the opposite, such as don't drill deeper than 300 feet due to hard rock formations in the area, or local ordinances that prevent drilling into the aquifer. If you do end up changing the number of bores, go ahead and rerun the borehole model with an updated bore pattern. That will confirm the results instead of relying on an approximation. Some projects may have physical space constraints, such as buildings or property lines, which limit the number of possible boreholes. Even if the bores are not in a grid, we can still approximate the required depth for each bore by using the total bore depth result along with the number of bores that fit in that space. Some of the geothermal software packages can handle irregular borehole layouts like this. Now that we have an overview of the process, let's take a closer look at how the value of total borehole depth is calculating. Understanding the sizing logic will reveal which levers can be adjusted to fine-tune the size of the ground heat exchanger. The process starts out with the heating and cooling loads for the building. These loads are generated from an energy modeling software such as Trane Trace. Compressor heat adds to the building heating and cooling loads, resulting in a total load profile experienced by the ground. The ground modeling software uses heat pump performance curves to make this adjustment. The heat load on the ground causes it to heat up and cool down. The change in temperature depends on the ground properties and the Borefield construction. As the ground temperature changes, so does the heat pump entering water temperature. This in turn affects the heat pump performance. By setting an upper and lower limit on the heat pump entering water temperature, we ensure that the heat pumps operate reliably and with good efficiency. The total borehole depth value is based on keeping the heat pump entering water temperature within the specified limit range. The hourly load data on the left shows winter heating loads and summer cooling loads. During cooling season, we're rejecting heat to the ground, so the temperature goes up. And in heating season, we're pulling heat from the ground, so the temperature goes down. The chart on the right shows the calculated fluid temperature entering the heat pumps. Notice that this project has a slight increase in temperature at the end of the year compared to the start. Let's call this temperature drift. Since geothermal systems are designed for many years of reliable operation, the year-over-year temperature drift must be considered. For this example, we're looking at a 20-year window for sizing the Borefield. The blue line is the average entering water temperature for each month, gray is the maximum value, and orange is the minimum. The heat pump entering water temperature limits are set at 40 degrees and 90 degrees. The Borefield sizing software calculates a total depth value needed to stay within these temperature limits for the specified window of time. In this example, we touch the upper limit at month number 235. As we just saw, the heat pump entering water temperature limit plays a direct role in the ground heat exchanger size. So what happens if we move the limits a bit? Extending the limits by 5 degrees in each direction causes the Borefield sizing to recalculate with a smaller value. Now we get 299 feet of bore instead of 325. Or alternately, we could keep the original depth value and reduce the number of bores from 120 to 110. Note that for this example, the system is constrained by high temperature, not low temperature. So extending the lower limit down didn't make much difference. Systems that are heating dominant will be constrained by the lower temperature limit and may benefit from heat pumps with lower temperature ratings. Like most engineering decisions, there are trade-offs. Heat pumps that operate with wider range of entering water temperatures will have higher compressor lift and therefore lower efficiency. Remember that the whole sizing process started out by assuming a value of thermal conductivity for the Earth. That assumption has direct consequences on the system performance, so it's a good idea to check our assumptions with a thermal conductivity test. The test is conducted by installing a complete bore with the expected materials and construction specs. Larger jobs with hundreds of bores may install multiple test bores to check for variation in thermal conductivity at different locations. Water is pumped through the bores, and heat load bank adds a constant amount of heat to the bore for about 2 days. Temperature sensors record the water temperature into and out of the bore. The resulting temperature profile has an inverse exponential decay, and the curve fit for it yields the thermal conductivity value. Thermal conductivity testing is all about reducing project risk. Having a calibrated value of thermal conductivity improves the modeling capability so we don't end up with an underperforming bore field. The test bore could also reveal drilling issues that pose project schedule risk. There's other ways to reduce project risk, such as leaning on the experience of local drillers, using online well drilling logs, or adding design margin to the project schedule and budget. But given the cost of installing a geothermal system, our suggestion is just to do the thermal conductivity test. John, I think it's time that we switch gears and start talking about heat pumps. Could you start us out?
Yeah, thanks, Ben. Next, we'll move on to discuss the heat pump equipment itself. Heat pumps that use geothermal can generally be grouped into 2 categories, distributed or centralized. A distributed geothermal system is the classic approach in which smaller water source heat pumps are spread throughout the building, each installed in or near the zone it serves. And then a common distribution loop connects them all together along with the ground heat exchanger. Now, while either approach can be used in most building types, distributed geothermal systems are commonly found in schools, apartment and condominium buildings, dormitories and barracks, and extended care facilities. In contrast, a centralized geothermal system uses chillers or heat pumps located in a central plant. And then chilled water or hot water loops are used to supply various types of airside equipment. Centralized geothermal systems are also used in many types of buildings, but are probably most prevalent in larger buildings like schools, campuses, office buildings, industrial and medical clinics. Now, both can provide excellent efficiency, but have their own advantages and considerations. A distributed system often has a limited need for floor space for mechanical equipment. Small heat pumps are often installed in the ceiling plenum or in a closet near the zone. The equipment is easy to service, leading many owners to take that on themselves. If a heat pump fails, the impact is isolated to just that zone it serves. And capacity can be easily added and incrementally funded, assuming, of course, that the Borefield was sized for that added capacity. The piping design is relatively simple, and the refrigerant charge at each heat pump is relatively small, making it easy to comply with safety codes. But this distributed approach also has some unique considerations. Service and maintenance often must occur in or near the occupied spaces throughout the building. This can be a productivity issue and a nuisance for occupants. Acoustically, noise-generating equipment is located close to the space, which limits attenuation options. A separate dedicated outdoor system is required for proper ventilation and humidity control, and small packaged heat pumps usually have limited options for enhanced air cleaning. Now, as for centralized systems, many of the advantages and drawbacks are counter to what I just went through for distributed systems. Service and maintenance is mostly centralized, occurring in separate mechanical rooms. This keeps service personnel out of the occupied space. Noise-generating equipment is further away from the occupants, so there's more options to attenuate the sound. And centralized air handlers usually have more flexibility and more options for enhanced air cleaning. Now, on that theme of flexibility, a centralized geothermal system can pair with almost any type of airside equipment, from fan coils to air handlers. And using fewer centralized heat pumps often makes this the more attractive choice for many larger scale buildings. And finally, the centralized heat pumps can be sized based on the block building load, which results in fewer installed tons than simply summing the peak loads of all the zones, like with distributed heat pumps. But a centralized system also has its drawbacks. This approach requires some building floor space for mechanical equipment rooms. And the heat pump chillers typically require a trained outside technician for servicing. Redundancy must be purposely designed into the system to limit the impact of equipment failure. And the central heat pump equipment has a larger refrigerant charge than the smaller distributed units. However, this charge is isolated away from the occupied spaces. Now, we previously produced an E&L on the distributed heat pump systems, which is listed in your bibliography. So today, Dan is going to focus on centralized heat pump equipment and system configurations. Dan?
Thanks for the refresher on distributed and centralized geothermal systems. As John mentioned, because we already produced a program on distributed heat pumps, today we will focus on centralized systems. Now, let's dig into the central plant options in more detail. First, we will look at two-pipe changeover systems for modular and packaged chillers. Next, we will spend more time on four-pipe distributed systems. Again, we will look at modular chillers, followed by several configurations with packaged chillers. Later in the program, we will look at some hybrid-type systems that include storage, energy recovery, thermal energy networks, and cascaded or booster aspects. The first aspect of the plant design we will consider is the distribution type. Two-pipe changeover systems, as the name implies, have two pipes, one for supply and one for return, and the system operates in either heating or cooling mode. Switching modes is called changeover. Here we see a simple decoupled system operating in heating mode via a boiler. I'm not showing geothermal yet, just want to talk through the distribution first, and then I'll add the geo. One of the major drawbacks for changeover systems is determining when to change from one mode to the other. Changing modes is energy intensive, and comfort is likely sacrificed leading up to and until changeover is completed and the system is caught up. In a traditional changeover system, a chiller may provide cooling in the summer while a boiler provides heating in the winter, using the same set of pipes. In this mode, the boiler has been disabled and the chiller is now running, changing the system mode to cooling. Today, heat pumps allow for system designs to use a single piece of equipment for both heating and cooling operation. I mentioned a simple decoupled system with the previous diagrams, so let's look at that in a little more detail. Packaged and modular units have different flow control strategies and limitations that need to be considered. In this example, we have a single 120-ton packaged air source heat pump and a 120-ton modular air source heat pump consisting of 4 modules. Both units are selected at the same fluid and ambient conditions. As you can see, most of the performance characteristics are pretty similar except for one key item, the minimum flow rate. For the packaged heat pump, the minimum flow rate is 73% of design for cooling and 87% of design for heating. Recall that when considering a variable primary flow system, the target minimum flow rate should be 50% or lower. The minimum flow for the modular heat pump is all the way down to 25% of the design, meaning it would be a great candidate for variable primary flow, while the packaged unit should be implied in either a constant flow system or a decoupled pumping system. With that understanding of two-pipe changeover systems, let's look at some units in geothermal systems. First up is a modular reversible heat pump. The assembled bank of modules operate in either cooling or heating mode of operation. All modules are in the same mode of operation and change over together. Operationally, these units reverse the direction of the refrigerant within the unit by a 4-way reversing valve. This means the load heat exchangers are always connected to the building load, and their role can change from evaporator in cooling mode to condenser in heating mode. The same applies to the source heat exchanger. Its role is dependent on what mode the unit is in. With changeover heat pumps, when the unit changes over, so does the system. Packaged units are also applied in two-pipe changeover systems, but the system components and application of them is different than that of a modular heat pump. Because today's packaged units do not typically contain a reversing valve, which would allow for them to change over, we must change over the fluid system instead. One way this can be done is by including a 3-way control valve on the geothermal line leaving the Borefield, connecting the Borefield to the load loop, with another one at the leaving evaporator, again connecting to the load loop. In heating mode, the fluid leaving the Borefield enters the evaporator where it is cooled and sent back to the Borefield. And the last 3-way valve is after the load, connecting it to the hot water loop. When the system is in cooling mode, the 3-way valves are positioned such that the fluid leaving the Borefield enters the condenser, where it is heated up, and that heat is rejected back to the Borefield. These systems would generally be constant flow for simplicity, but could potentially be variable flow depending on the flow limitations of the equipment. Capacity turndown should also be considered here, as with any single unit application. One design aspect we need to touch on here is head pressure control. This control is required when units are operating in cooling mode and the available geothermal fluid is cold or below a minimum entering temperature to maintain the required compressor pressure differential. This can commonly be achieved via pump speed control or throttling valve and may be a standard feature for some unit controllers. Now that we understand some of the nuances of two-pipe systems, let's shift gears to 4-pipe distribution systems. Coming from our central plant, we have a loop for heating and a loop for cooling. Depending on the design of the centralized equipment, these loops may be dedicated, meaning they do not mix with one another, or there can be mixing of fluid loops when the unit changes modes or different unit types are used together. We will look at both system types coming up. Both modular and package units can be used in 4-pipe distribution systems, and again, they each have their own distinct considerations. We will look at modular systems first, followed by some packaged configurations. Over the years, modular units have become very popular for smaller scale geothermal projects, largely driven by their designs aimed at geothermal applications and their compact nature. One of those popular units is the multi-pipe unit. Multi-pipe units can be commonly characterized by having 3 separate heat exchangers, one dedicated for cooling, one for heating, and the third connected to the Borefield, which changes roles based on the mode. In this unit, we see there are 3 braze plate heat exchangers. The individual modules can operate in either cooling only, heating only, or simultaneous heating and cooling. When modules are coupled together, they will operate in simultaneous heating and cooling whenever a simultaneous load exists. After that, the additional modules are available in either heating or cooling dominant mode. Please see Trane.com for more product details. I mentioned head pressure control a bit ago, and that is still important with these machines, but looks a bit different. With the multi-pipe units, this feature is built into the unit. There are automatic motorized control valves on the source sink side of the unit that will begin to modulate or pinch down to maintain the required compressor differential pressure whenever the entering source fluid is below a threshold. A key system advantage to this design is that all 3 loops are independent, meaning there is no mixing of fluid loops. This means that different fluid types can be used in each loop. Maybe the design calls for 30% propylene glycol in the geothermal loop and water in the heating and cooling loops. Not a problem for this design. Another benefit in the system design and operation is that the loops do not have the same design and operating pressure, or any loop equalization measures would need to be considered for that systems that do mix fluid types. The pumping systems can be decoupled as shown here, or could be variable primary flow. Keep in mind that with modular units that contain automatic isolation valves, the flow through the unit will be variable, so in decoupled pumping systems, all sets of pumps will be variable speed. Modular units can also be combined with package units to optimize the cost and performance of the system. More to come on that later. Now that we understand multi-pipe modular units, let's move on to packaged units in 4-pipe distribution systems. The first major difference here is that a packaged unit does not contain a reversing valve. So as previously discussed, we must design a system that can change over because the unit does not have this capability. First, let's look at a single unit system. Similar to the 2-pipe system, we see the inclusion of a 3-way control valve that connects the fluid leaving the Borefield to the entering evaporator and entering condenser lines. Operationally, the system controls will control the unit to the larger of either the heating or cooling loads. When the system is commanded to operate in heating mode, the unit controller will control to the leaving condenser fluid temperature. The 3-way valve is positioned such that the fluid leaving the Borefield is directed to the entering evaporator of the heat pump, where this fluid is cooled down and sent back to the Borefield. Cooling mode would change the process over, sending chilled fluid to the cooling load and sending the rejected heat to the Borefield. So what about simultaneous mode? When the system is commanded to operate in simultaneous cooling and heating modes, one more item needs to be defined, and that is the priority. Here we see a demand for both heating and cooling, with the cooling load being larger than the heating, thus cooling priority. The unit controller will control to the leaving evaporator fluid temperature. The 3-way valve is positioned such that the fluid leaving the Borefield is directed to the entering condenser of the heat pump, where this fluid is heating up and sent back to the load and then back to the Borefield. This is how the fluid loops mix. Something to point out here is that when there is simultaneous demand, the unit needs to operate at the design cooling and heating temperatures, meaning that, for example, in cooling mode, the system cannot benefit from cooler source temperatures as can be achieved in other central designs. I mentioned that the fluid loops in these systems will mix with one another, and it is this switching of modes via the position of the 3-way valve that makes this happen. When in heating mode, as shown here, the evaporator loop interacts with the geothermal loop. And in cooling mode, the condenser fluid interfaces with the geothermal loop. So when these systems change mode, all 3 loops eventually mix together. If mixing must be avoided, then isolation heat exchangers could be implemented on the chilled and hot water loops. Naturally, the next configuration builds on the previous by adding multiple units and adjusting the system design a bit. With this configuration, motorized isolation valves are included at the supply side of each unit. These valves are open when the associated unit is on and close when the unit is off. Additionally, motorized isolation valves are included on the headers for the chilled and hot water main return lines. With this configuration, whenever there is a simultaneous demand, one or more units will be operating in simultaneous heating and cooling mode, while the other available units can be utilized for either heating or cooling dominant. If that sounds familiar to how the multi-pipe unit operates, it's because it is very similar from a simultaneous heating and cooling dominant mode delivery. Let's look at this system operation in a little more detail. Here we have a hypothetical load that requires 3 units worth of heating and only 2 units worth of cooling. The details here lay in how the valves in the plant are positioned based on the system needs. Since the heating load needs all of the heat the plant can provide, all of the valves on the condenser side are open. Notice there is no geothermal flow on the condenser side of the plant. On the evaporator side, all but one valve are open. It is this boundary valve that isolates the chilled water loop from the geothermal loop, meaning the evaporators above this valve will supply chilled fluid to the cooling load, while the unit or units below the valve will be sourcing BTUs from the Borefield to support the unit operating in heating mode. With the valves in this position, the top 2 units are operating in simultaneous heating and cooling mode, while the lower unit is operating in heating mode. I teased this a bit ago, and here we are now, mixing modular units with packaged units. It is commonly understood that modular units have a higher first cost compared to packaged units, and rightfully so, because they come packed with features and benefits. So, it's easy to deduce that trying to limit their use, however effective, is common when it comes to rounds of budgeting and costing, so mixing them with packaged units makes a lot of sense. This plant will be sized for 300 tons and consists of one 150-ton multi-pipe unit and 2 150-ton packaged heat pump chillers. The idea here is that the modular unit can easily handle the relatively small simultaneous loads, and the heat pump chillers can handle the either dominant heating or cooling loads above that simultaneous point, and do so in an efficient way, both operationally and first cost. The pumping system will be decoupled with dedicated pumps per chiller, and for good reason. First, the modular unit and the packaged units will likely have different pressure drops. Going with dedicated pumps simplifies this operation. As previously mentioned, the modular unit is variable flow by design, so those pumps need to be variable speed. The heat pump chillers do not require variable flow, so they will have constant speed pumps, again for simplicity. Let's review some advantages and considerations for our plant with mixed unit types. We could consider a plant solely comprised of multi-pipe units, but in a larger system, this tends to get rather expensive. By reducing the number of modular units and mixing in some packaged units, our first advantage is reducing the cost of the equipment. Next, by using larger packaged units, we can reduce the total number of units and components in the system. For example, if we replace one multi-pipe unit that has 3 modules with one packaged chiller, we reduce the number of heat exchangers by 7 and the number of compressors by 4, not to mention several valves. With packaged chillers, we have more compressor options like screw and centrifugal, as well as shell and tube heat exchangers. And unit sizes range from a few hundred tons to several thousand. With more units to choose from comes more efficiency options and unit optimization. A benefit of having a modular unit in this system is its ability to turn down lower than the packaged units, in terms of both capacity and flow. And of course, the flexibility in multiple modes of operation of the multi-pipe unit is beneficial. But there are some system design considerations for this type of mixed plant. The first one is a limit on the design hot water supply temperature. It's limited by the unit with the lowest achievable temperature, in this case 135 degrees from the multi-pipe unit. And with how the heat pump chillers are connected to the heating, cooling, and geothermal loops, all three fluid loops will mix. And last, as can be expected, is increased complexity in the system controls. In summary, we reviewed the differences between 2-pipe and 4-pipe distribution systems and how changeover units differ from changeover systems. We looked at how to use different unit types, packaged or modular, in various system types and various quantities of units. And we talked about systems that allow for all three fluid loops to mix and one that does not. Finally, we wrapped up with a central geothermal system consisting of packaged and modular units to optimize the first cost. Back to Ben.
One of the sticking points with geothermal is project cost. In this section, we'll look at an example project and consider system choices that could help the project pencil better. The project is a 2-story office building in climate zone 5A with a central geothermal system. This project will use a vertical bore field and a central heat pump plant designed to handle peak loads of about 200 tons of cooling and 1,800 MBH of heating. Today, we'll consider the impact of using heat pumps with wider operating temperatures, changes to the bore-to-bore spacing, the value of specifying a premium grout for the boreholes, and whether adding a cooling tower to supplement the heat rejection to the ground would help. For each of these choices, we're looking for reduction in the Borefield install cost, and we're thinking about potential trade-offs against the long-term system performance. The first option is selecting heat pumps with wider ratings on the entering water temperature. Recall from earlier that Borefield sizing is calculated to keep the heat pump entering water temperature within a specified range for the design life of the project. Allowing a wider range of entering water temperature results in a smaller Borefield. For this project, we started out with an upper temperature limit of 90 degrees. By increasing the upper temperature limit by 5 degrees, the ground heat exchanger could be downsized by 8%. Further downsizing is possible, but the project team is concerned about giving up too much system efficiency. So we're going to settle on a new design limit of 95 degrees heat pump entering water temperature. The trade-off with this option is that higher heat pump entering water temperature means higher lift conditions, so the compressor must work harder and the efficiency is lower. This can also affect the heat pump capacity, and in some cases, force you to upsize the heat pump in order to maintain design capacity. Next, let's consider the bore-to-bore spacing. We started out with a nominal value of 20 feet. Increasing the bore-to-bore spacing would give each bore a larger volume of dirt to work with thermally, meaning that the total bore field depth could be less. The trade-off is that spreading the boreholes apart means that the physical space used for the ground heat exchanger is larger. For this project, the drilling contractor uses 20-foot pre-cut pipe segments, so even though there is some benefit to increasing the bore spacing, this is offset by material and labor costs. We decided to stick with the initial value of 20 feet. Next, enhanced grout improves the thermal conductivity from the bore pipes to the ground. Better thermal conductivity from the grout reduces the bore field size. The trade-off is simple. Premium grout costs more. For this project, we started out with a high-performance grout, 1.2 BTUs per hour per foot per degree. This is already a premium performance grout, and we decided to just stick with it. Finally, let's look at the effect of balancing out the heating and cooling loads. This is one of the bigger levers that designers have to optimize bore field size. Seasonal load balance is achieved when the annual heat rejected to the earth is equal to the annual heat sourced from the earth. There are two fundamental options to manipulate the amount of heat rejected to the earth. we can either change the load demand, or we can modify the central plant design with a supplemental heating or cooling device. The load demand can be tweaked with things like upgrades to the building envelope, lighting, or ventilation. Some upgrades, like improvements to the building envelope, may lower both the heating and the cooling demand, while other changes, such as upgrades to lighting, may lower the cooling demand while increasing the heating demand. If changes to the building design are out of scope, then supplemental heating and cooling equipment may be added to the system, such as a cooling tower or a dry cooler, or an air-cooled chiller, while a boiler may be used for supplemental heating. Let's take a closer look at how supplemental cooling or supplemental heating devices should be added to a geothermal system. Cooling towers are typically piped downstream of the ground heat exchanger, allowing the warmest water in the system to go to the ground first. This maximizes capacity of the ground heat exchanger, which is typically the goal. Note that a closed-circuit cooling tower should be used to avoid contamination of the ground loop. Supplemental boilers in geothermal systems are typically installed in the hot water distribution loop downstream of the heat pumps. This allows the boiler capacity to supplement the heat pump capacity during peak heating loads. The project that we've been analyzing is cooling dominant, and we'd like to reduce the amount of heat that's rejected to the earth. The chart on this slide shows what happens to the total bore depth when building cooling loads are reduced. As one would expect, smaller cooling loads result in smaller bore fields. Similar results could be achieved by rejecting some heat to a supplemental cooling tower instead of the bore field. One interesting thing about this project is that reducing the cooling loads by more than 20% does not result in further decrease to the total bore depth. Why is that? Once the cooling load is reduced enough and the loads are balanced, then additional reductions do not help. Remember, load balancing is about flattening the temperature drift curve. If you go too far, the system becomes heating dominant and the bore field size is based on the lower heat pump temperature limit. Recapping a few points from the Borefield optimizations, designers have several levers that can affect the size and cost of the ground heat exchanger installation. Perhaps the biggest lever is the heating and cooling load profile. Building upgrades, supplemental coolers, or supplemental boilers can significantly reduce the required bore field size. Using heat pumps with wider temperature range can help bore field sizing, but at the expense of system efficiency. The bore construction specs, such as spacing, grout type, can be used to reduce the bore depth or bore count. And finally, the drilling contractor may have valuable input when finding the balance between performance, material cost, and install labor.
When I talk to engineers about central geothermal systems, one of the things they are worried about is the bore field becoming saturated or depleted. What happens if the ground temperatures get out of range, and what can building owners do about it?
The bore field sizing for any project is based on design conditions, which are based on assumptions. Maybe the design assumptions are off, or maybe the building usage has evolved over time. If too much heat is rejected to the ground and it becomes saturated at high temperature, then heat pump capacity may be limited or over-temperature trips could happen. Similar results can also happen if too much heat is pulled out of the ground and it becomes depleted at low temperature. This could be the result of slow year-over-year drift, or there could be an operational issue that causes large seasonal swings. Fortunately, the process is slow enough that if we're paying attention, we can take corrective actions. Let's start out with saturated ground temperatures. For systems that are saturated at high temp, the heat pump cooling operation is impaired, meaning that the chilled water set point isn't satisfied or the heat pumps may trip off on high condenser temperature. The good news is that warm ground temperatures are great for heating seasons, so let's focus initially on getting through the rest of the cooling season. That might be enough to get the system back on track. Start by limit the amount of additional heat that's rejected to the ground. If the system includes a supplemental cooling device like a cooling tower, then use it. An air-cooled rental chiller could be a good option to get through the cooling season. To keep existing geothermal heat pumps online, consider resetting the chilled water temperature by a few degrees to reduce the compressor lift. One might also consider higher flow rates in the heat pumps to reduce the delta T, but keep in mind that the additional pump energy adds heat to the ground, and we're trying to limit that heat rejection. To find a long-term solution, we need to know the root cause. If system operational issues are to blame, then let's get the system back to operating as designed. Otherwise, we need ways to manage the year-over-year temperature drift profile by reducing the cooling demand or by adding a supplemental cooling device. Some people get creative when balancing their heating and cooling loads. For example, an ice melt system in a parking lot might be exactly what this project needs. If the ground temperature is depleted, heat pumps may be limited in heat mode, or they could trip off on low evaporator temperatures. Cold ground temperatures are good for cooling season, so again, let's focus on the immediate problem of getting through the heating season. If a supplemental boiler is installed, that can make up for the limited heat pump capacity. Hot water reset can keep heat pumps online by reducing the compressor lift. Increased ground loop flow rates can help the heat pumps by reducing the evaporator delta T, and that added pump energy acts as a source of heat for the depleted ground loop. Long term, we need to find ways to add additional sources of heat to the building or reduce the heating loads. Long-term management of ground temperature is a slow process entailing small adjustments to the system operation from one year to the next. A skilled operator might make these tweaks intuitively. System controllers can be configured to adjust system operation based on the year-over-year temperature drift. And looking ahead, AI software packages will be used to optimize HVAC system operation real-time, including ground loop temperature management. To summarize Borefield temperature management, if the ground temperatures are saturated, the heat pumps may be limited in cooling mode. We need to reduce the cooling demand or find a different place to reject heat to. If ground temperatures are depleted, the heat pumps may be limited in heating mode. We need to reduce the heating demand or find other sources of heat. In both scenarios, focus on getting through the season and identify the root problem. Once a ground temperature management strategy is put into place, ground temperatures can be restored.
Okay, to wrap up this ENL, we wanted to introduce a few newer system configurations and trends in geothermal. So Dan, why don't you go first?
Our first system concept is adding thermal energy storage to a geothermal system. A big driver for this is reducing the cost of the system. Thermal storage tanks are significantly lower cost than drilling bores. The tanks could be integrated into the geothermal loop and used with or without the geothermal loop. Maybe a Borefield loop was undersized and tanks can be economically added to the system to bring it back into ideal operation. Careful attention must be paid when it comes to controls to balance the field loop and the tanks. Exhaust recovery is another potential modification to a geothermal heat pump system. For heating-dominant buildings, recovering heat from exhaust air can reduce the heat sourced from the ground, further reducing the ground heat exchanger size and cost. For cooling-dominant buildings, rejecting heat to exhaust air can reduce the heat rejected to the ground, reducing the size and cost of the Borefield. This can also boost the peak cooling capacity by false loading the heat pump chillers. Wastewater is another energy recovery opportunity. Buildings that drain high amounts of heated water are ripe with opportunity to recover heat that could be directed to the Borefield and to the building being served by the system. Again, this could help reduce the size of the Borefield and/or help maintain an ideal Borefield temperature.
All right, Ben, tell us about thermal energy networks.
Thermal energy networks are a way for multiple buildings in a district or a community to share heating and cooling resources. Unlike district plants that supply hot water and chilled water to each building, thermal energy networks use an ambient loop. The ambient loop may be built with a supply and return pipe to each building, or a single pipe arrangement may be used, with each user rejecting heat to or pulling heat out of the loop. Thermal energy networks make the most sense when the users connected to the loop have diverse loads. In this way, heat rejected from one user can be recovered by the next user. The other benefit is that expensive capital equipment, such as a geothermal Borefield, can be shared by many users, making it more affordable for each user. New laws pertaining to geothermal system leasing could make it easier for third parties to install and operate these resources, turning huge development costs into a monthly charge for each user or the thermal network operator.
Okay. Dan, how about high temperature needs for heating?
Traditionally, geothermal systems have been limited to lower hot water supply temperatures, generally under 140 degrees. When additional lift, i.e. hotter supply heating water temperature or colder source water, chillers can be arranged in a cascaded configuration to increase the overall lift capabilities of the system. Many existing heating systems are designed for high temperature heating hot water, often in the 180 degree range, and in many cases, those systems must remain in place while heating plants will come and go. So cascading units to achieve the required lift is one way to do this. How this works is the low temperature unit provides chilled water for the cooling loads and can source energy from the Borefield when the system is in heating mode. The condenser of the low temperature unit feeds the evaporator of the high temperature unit, which makes up the intermediate loop. The intermediate loop can also reject heat to the Borefield. The high temperature unit is then controlled to maintain the heating loads. This system concept could also be beneficial if very cold source temperatures are present in heating mode, meaning more lift is helpful.
Finally, once the equipment is selected and the system is laid out, how about operational decisions that can affect system performance?
Geothermal system efficiency is a combination of heat pump energy, fan energy, and so forth. One way to improve the system performance is by finding the optimal speed and flow rate for the ground loop pumps. This concept is similar to cooling tower optimization. Lower flow rate through the ground loop results in less pump energy. At the same time, lower flow rate means higher delta T on the heat pumps, which raises the compressor lift and increases the compressor energy. The sweet spot for ground loop pump speed will depend on the system differential pressure. A higher system DP uses more pump energy, so we can save more energy if those pumps are turned down. This example analysis uses a Trane RTWD heat pump chiller and a system DP value ranging from 30 to 60 feet of head. It shows an optimal ground loop flow rate between 2 and 2.4 GPM per ton. This translates to ground loop delta T of 10 to 12 degrees, depending on the system DP. Earlier, we talked about Borefield temperature management. If the Borefield is running hot, then optimize on the side of less pump energy. And if the Borefield is running cool, then optimize on the side of more pump energy.
Thanks, team. We hope you found the information helpful. Today, we reviewed the various types of ground heat exchangers that are available, depending on your project's constraints, and also demonstrated the sizing process using one of the available software tools. We then compared distributed versus centralized approaches to applying heat pump equipment and walked through several central heat pump plant configurations. Then we demonstrated how system optimization can reduce the size and cost of the Borefield, and shared strategies for managing Borefield temperature drift over time. And finally, we briefly introduced a few newer system configurations and trends in geothermal. So please fill out a survey and let us know what you thought of today's program. As always, the bibliography included in the handout provides more information on where to find a number of resources related to today's topic, including the latest engineer's newsletter, all available free 24/7. Or contact your local Trane account manager for specific information on Trane systems, equipment, controls, and services. For those of you seeking continuing education credit, check out the newest online courses at the Trane Education Center. And finally, for those of you viewing in person, please ask your local host about details for upcoming Engineers Newsletter Live programs, or check them out at trane.com/ENL. And we launched a new podcast early last year, hosted by our very own Dan Gentry and Charlie Jellin. So please check out Cool Air Hot Takes on your favorite platform and subscribe. Thanks for joining us today. We look forward to seeing you next time.